We're in Rosen, section 10.4 on graph connectedness, and now we discuss some definitions related to connected graphs. If we have a connected graph and there is a vertex that causes the number of disconnected subgraphs to increase, that is called a cut vertex. And if you have an edge, that if you remove that edge, the number of disconnected subgraphs grows by 1. That is called a cut edge. On a vertex cut, or separating set, is a set of vertices that if we remove them from our graph, the graph is disconnected. So a cut vertex is a vertex cut, but if you don't have a cut vertex, then you should be able to find a vertex cut of your graph that will cause it to have an increase in the number of disconnected subgraphs. And vertex connectivity, kappa of G, is the minimum size of a vertex cut. And if G is non-complete, that is true if G is non-complete. For complete graphs, the kappa of K sub n is defined as n minus 1. So a graph within vertices that is not complete will have a vertex connectivity of n minus 2 or less. An edge cut is a subset of the edge set such that G minus the edge cut is connected. If you have a cut edge, that itself is an edge cut, but if your graph doesn't have a cut edge, you can find enough edges to disconnect the graph, increase its number of disconnected components. And the edge connectivity is similar to the cap of G. Lambda of G is the minimum size of an edge cut of G. And then it's important to note the relation of kappa of G and lambda of G. If I have an edge cut, I can achieve that edge cut by removing some vertices associated with one end of those. So my kappa of G is always less than or equal to lambda of G because sometimes I might be able to take out several edges with one vertex removal. And also note that lambda of G is less than or equal to um, the degree of the minimum degree vertex. And that's because if I can remove all of the edges from that vertex, I've disconnected that vertex from the rest of the graph. Let's take a look at some examples. Graph G1 has both an edge cut or a bridge and also a vertex, a cut vertex. And so a cut edge is a bridge and a cut vertex will also disconnect this graph. G2 has no bridge or cut edge, but it does have a cut vertex. If I remove C, then I'll have disconnected components. So I'll go back to G1. The kappa of G1 is 1, and the lambda of G1 is equal to 1. Here, kappa is equal to 1, but lambda is equal to 2, because I could remove this edge and that edge and isolate A. All right, for this G3, I have no cut vertex, but I can see that if I remove BC and FG, then I'll have created disconnected components. So my edge cut is 2, and that's also the same as my edge connectivity is 2, so lambda equal 2, and my vertex connectivity is also 2. I could remove C and F, so kappa is equal to 2. For G4, my lambda goes to 3. There's every one of these edges has at least degree of at least 3, and I don't see any way that I can remove less than 3 edges and disconnect the graph. So if I remove BA, BG, BC, all have isolated B, but there's no other way to come up with an edge cut that's less than 3. So here I have lambda is equal to 3. However, there is a vertex cut that's less than that. If I remove F and I remove C, that'll be an induced graph that has increased number of disconnected components. So kappa is equal to 2. And I believe the min vertex degree is 3. And then this last one, G5, it also has a lambda of 3 because you can see that A has a degree of 3. It turns out in this one that there's no way to achieve disconnected components with only 2 vertex removals, so kappa is also equal to 3. And that's our discussion of vertex and edge connectivity.